From A, we know that the shifted measure is sufficiently pleasant to allow for our random walk to have negative drift and therefore achieve ruin with probability 1, which means in almost every sample path. That is nice because what we now want to do is find an expression for the probability of ruin in terms of our shifted measure, because then we can just simulate under the shifted measure and use that to find an estimate for our ruin probability. And that expression that we want to find is given by this in the exercise text, where the TU is the time of ruin. So STU is the value of S at the time of ruin. We're actually asked to show two things in the exercise. First, we're asked to show that this holds, and then we're asked to show that it implies the Lundberg inequality. And I think we should start with the easy part, the fact that this implies the Lundberg inequality, because, well, that is just the easiest to show. So Lundberg inequality. So recall that the Lundberg inequality tells us that the probability of ruin has an upper bound given by e to the r to the e to the minus ru, right? So it's e to the minus r multiplied by the initial capital. And we want to show that this implies this. And what you can see is if you find out that the ruin probability is given by this expectation, well, then you know that at the time of ruin, by definition, S at that time must be smaller than minus U. So the mean value of this entire thing is smaller than the mean value of e to the minus u multiplied by r. And what we now have is just something deterministic equal to e to the minus ru. So the Lundberg inequality follows rather easily from the result that we have in B. So now let us try to show this result in B. In order to do that, we have to go into the exercise text, which is quite lengthy and wordy, and consider what they write. So they tell us, start by writing down a representation of the probability that ruin occurs at time k. So the probability that ruin occurs at time k according to the exercise can be written as psi k of u equal to, well, what they essentially then do is they consider the set bk of outcomes for these increments that result in ruin. And they say, well, consider these outcomes and measure the probability of the event of these outcomes. So this set of outcomes bk is defined as those increments which result in ruin at time k. And what we mean by that is those outcomes that result in ruin occurring exactly at time k. There are some observations that are quite nice when we consider this bk. And one thing that you may notice is that b1, b2, b3, and so on, they are all disjoint. They are disjoint sets. And the reason for that is, well, you cannot have ruin occurring exactly at time 2, for example, and also occurring exactly at time 3. If you have some outcomes of these increments which let ruin occur exactly at time 2, well, then those outcomes belong in B2. Because if they belonged in B3, then ruin would not occur until time 3. So B1, B2, and so on are disjoint sets, which means that, well, it means that if we consider the entire family of BI, well, then that is a partition of their union. Okay. And the reason why this is nice is due to a second thing that we may notice. Well, and that is, it is only in the case that our outcomes lie inside this union that the time of ruin is well defined. If you have an outcome that does not lie inside this union, then basically you have an outcome for the increments z1, z2, z3, etc., which does not result in ruin at any time, and in that case the time of ruin will be infinite. So therefore you actually have that the event that the time of ruin is infinite, well, this event is exactly the same as the event that ruin does not occur at any time, which is, well, these events are the events where you have ruin occurring at time 1, 2, 3, 4, so it's the complementary of this thing here. And that is quite nice because I mean, that also means that the event that TU is well defined is just given as the union of these outcomes. So that allows for us to get the time of ruin inside our expression right in the moment where we want to write something up. So let's just start by writing up what we have. We want to calculate the probability of ruin, and the probability of ruin at any time point is just the same as, well, the probability of ruin at time 1 plus the probability of ruin at time 2, 3, 4, 5, and so on. So you do that by summing the psi k's, and each of the psi k's are expressed using mu. So let us now try to express them using mu tilde. So by abstract change of measure, you have e to the ry, not ry, rz1, d mu tilde z1, and then e to the rz2, d mu tilde z2, and so on until e to the rzk d mu tilde zk. Okay, so what we can do is we can gather all of the exponents together and notice that what we are just doing is we're taking the mean value of something with respect to the measure mu tilde. But then we also restrict that mean value to bk. So what we have is the sum from 1 to infinity of the mean value with respect to mu tilde of e to the rz1 plus z2 plus and so on up until zk, restricted to bk. And what we mean by this e tilde is we mean that each of the z's are distributed have distribution mu tilde. So zi each mu tilde distributed. And now we can make use of what the definition of bk is, which is you have ruin exactly at time k, because the nice thing here is then that, well, let's first start by denoting the sum of increments by s, And typically we would just write k here, right? But instead of writing k, what we can notice is that, well, we are restricting the mean value to bk. So we're only considering those outcomes where ruin occurs exactly at time k. So on this restricted set, we are actually we actually have that the time of ruin is k, and therefore k is also the time of ruin. So we may write STU here. And what we're then doing is we're actually summing, we're taking the summation of this mean value on all of these restricted sets bk. So what you actually have is the mean value of e to the r multiplied by the sum of increments at the time of ruin, restricted to the union of the bk's. And that is equal to e tilde of the mean value with respect to mu tilde of e to the r multiplied by s at time of ruin, multiplied by the indicator that, so we had this restriction, and that restriction is the same as this restriction, so multiplied by the indicator that the time of ruin is finite. Now, I know that in the exercise, they actually write the mean value of e to the rstu with no indicator here. And the reason why that is the case, well, is because think about it a little bit. What is the probability of tu being finite under the distribution mu tilde? Well, under the distribution mu tilde, the random walk has negative drift, which means that tu will then be finite almost surely. And therefore, we can just finish off here by removing this restriction. I mean, to be completely fair, we could also just have realized that all the way up here and not done all of this. So that was actually probably a waste of time. But I mean, it doesn't hurt. It's not the prettiest way to solve the exercise, but it is one way. So there you go.